Okay, so next up we have Kyle Lennon from MIT. Kyle's in the field of chemical engineering. His advisor is Patrick Doyle, and he did his practicum at my old stomping ground, the Sandia Labs in New Mexico. So I'll let you take it away, Kyle. Thank you.
We got on the mic? All right, cool. Well, it's good to be here with you all. Again, a little bit bittersweet to be my last year as a fellow here, but I'm excited to talk to you today about a little bit of the work I've been doing during my thesis, in particular to use a combination of machine learning and physics-informed models to simulate complex fluids. So if the term complex fluids sounds unfamiliar to you, that's okay. I assure you that these are materials that you interact with all the time. Maybe the first thing that you did this morning was use one to brush your teeth, and maybe after that, you used a couple in your morning skincare routine that you learned from TikTok, and after that, you might have eaten one, and maybe at some point today, you used one to sanitize your hands, and this is something that we all became intimately familiar with over the last few years. We know what makes a good hand sanitizer. Maybe you've gone into a restaurant at some point and used their special hand sanitizer, and it's been way too liquidy, and it just ran straight off your hands, and that's no good. And it's definitely no good if your hand sanitizer is too solid-like and you can't even rub it into your hands. You want it to be somewhere in between. So if you're, shearing it really hard, it should rub in pretty easily. But it also should kind of stay put on your hand just after you squeeze it so that you're able to, transition to the rubbing phase. And so that's sort of the purview of this field of rheology, is to understand the relationship between the stresses that we put in, the deformations that we get out in these complex fluids that are somewhere between a liquid and a solid. What makes this relationship so complicated and worth an entire field of study is that firstly, it's nonlinear, and secondly, it has this property that's interesting where the properties of the material at a certain time sort of depend on what's been going on in the recent past to the material. And really this results in very different looking properties based off of the time scale that we observe our materials in or that we deform our materials with. So the first step in understanding this relationship is, of course, to be able to characterize it experimentally. And so there's many, many ways in which rheologists will measure the relationship between stresses and deformations. And I'm just going to focus on one today. The setup experimentally is sort of like sandwiching a fluid in between a bottom plate and then a top coner plate. If we rotate this top fixture and the inertia of the fluid is negligible, then we set up this linear velocity profile in the fluid gap. And we're really interested in the slope of this profile, which is called the shear rate, and relating it to the force per unit area or the shear stress on the top plate. So for a purely viscous fluid, the relationship between the shear stress and shear rate is pretty simple to characterize. We just need some nonlinear function called a viscosity. But for a complex fluid, it's a little bit more complicated. And that's because depending on the features of this time-varying protocol with which we turn the top plate, we're going to get very different looking properties and different looking data. So for instance, if we use an oscillatory waveform to probe this material, we might characterize something called a complex modulus, which could depend on the frequency of that deformation or the amplitude. Or if we use a steady function to deform the material, we might characterize the viscosity as a function of the rate at which we're deforming it. If we use a transient protocol, which is like the startup of a steady flow, we might track the stress as a function of time. And so we get all this different looking data, and it's hard to make sense of. And so really, what we need to do in order to take these data and turn them into actionable insights to make models is to come up with some physics-informed constitutive equations to tell us what's going on. And so I think here it's good to focus on what actually is the scope of a constitutive equation in modeling a complex fluid. So first off, we think of some protocol when we're generating some experimental data with which we're going to deform the material. We use a set of instrumental equipment to actually impose that protocol on our fluid, and then we transduce the response to get some sort of output waveform. And then in a simulation, when we have a constitutive equation, what we really want is that the equation is just standing in for the fluid itself and none of the other parts of this pipeline, right? So the experimental equipment, that's handled by maybe boundary conditions or forcing functions in our simulation. And then the transduction step, that might be post-processing of our simulation. But the constitutive equation should just stand in for the model, or the constitutive equation should just stand in for the fluid, sorry. And why I say this is because, of course, there's a huge interest nowadays in using data-driven tools to replace the really expensive step of coming up with one of these constitutive equations from like physical considerations. But the machine learning constitutive equations that we have so far are really end-to-end. So they map directly from forcing function to data. And so they capture the boundary conditions and the post-processing all within their architecture. And this makes them really rigid. So we can't use a machine learning constitutive equation that's been trained on a certain type of data to predict other type of data, or maybe more importantly, to simulate a fluid in a scenario that we care about in industry. So here we would maybe want to plug our constitutive equation into a full 3D CFD solver, but we can't do that if it's too rigid. And so that's where this project comes in, is really to design constitutive equations that are capable of making this leap, going from data that we can get in a lab to simulations that we might care about in practice. And there are a few properties of this constitutive equation that I'd like to develop, which are very important. First off, it should be continuous time, so it shouldn't rely on some specific discretization of our protocols. It should be three-dimensional. It should be admissible, which I'll get to, but this is basically some sort of symmetry criterion for good constitutive equations that are physical. And then, of course, we should be able to train it on the data that we have on hand. So the first step in developing such an equation is to go way back to the basics. Maybe the simplest constitutive equation we can think of for viscoelasticity, which is just the combination of this Newtonian element and a Hookean element, which gets the liquid and solid-like features. We put them in series, we get something called a Maxwell model, which is this differential equation. And then the simplest thing we can do really maybe to make this a learnable constitutive equation, with machine learning, is just slap a neural network right in the middle of it. And being a fourth-year graduate student at the time, the simplest thing is exactly what I did. So that's where we start. And then we have this continuous time, one-dimensional constitutive equation. So that's still a problem because it's just 1D. So we need to take it and lift it into 3D. That's a pretty simple fix too. We just replace the 1D stress and the 1D strain rate by tensors. And these are two symmetric tensors called the stress tensor, the rate of deformation tensor, which is related to the velocity field. Okay, so now we have this 3D continuous time model with a learnable element. The next issue is a little bit more subtle, but we want this constitutive equation to be physical, which means that it shouldn't depend on the frame of reference that we're looking at our fluid in. Mathematically, that means that every term in this equation should commute with a time-varying rotation tensor. So there are really two terms that give us an issue. The first is the derivative, and the second is the neural network. There's plenty of work on how the time derivative can be modified to commute with such a tensor. And so we'll just borrow one of these materially objective tensors from the literature. And then the little bit more subtle point is how do we make a neural network to be frame invariant or to commute with this type of rotation tensor? Because if we just have the neural network act element-wise on all the elements of these tensors in general, it's not going to commute with rotation. So to do that, again, we go back many years to a nice paper that tells us, for arbitrary functions of two tensors, how can we make them frame invariant? How can we make them invariant to these rotations? It tells us that we can build this function as a polynomial expansion whose terms are just tensor products in the tensors that our function depends on. And so we enumerate all of those, and then we have coefficients, which I call G here. And these themselves can be arbitrary functions of what are called the invariants of these tensors. And you can just think of that like the trace of these tensors, which by definition commute with this rotation or are invariant to this rotation. Okay, so you might think, just this entire expansion, it might be infinite. It might not actually help us simplify the problem. But there's these nice closure relationships that come from the Cayley-Hamilton theorem, which actually close the set of tensor products and invariants to a really, really small number. And we can use this to build out this thing called a tensor basis neural network, which basically defines a fully connected neural network to get the coefficients of this expansion, then pairs them with tensors or tensor products. And out of that, we get a fully general but learnable and frame invariant neural network that we can stick into our constitutive model. And now, finally, we have a full three-dimensional continuous time learnable and frame invariant constitutive equation, which we call the rheological universal differential equation, or RUD. So the next part that I have to show you is that we can actually train these on real data. This is not actually too hard. Just like when we're generating experimental data, we choose a forcing function. We use that forcing function and knowledge of the flow kinematics to build the tensors of the strain rate and the stress tensors, and we just solve for the remaining elements using our model. We get out some predicted data, which we can compare to our experimental data via a loss function that might be like the mean squared error between those two things. And we can do that for very different looking forcing functions. And then we can combine all of our data into one global loss function. So we can train our model on data that look quite different, which is already unique for machine learning constitutive equations. And so you can sort of see that this RUDE framework fits in exactly for what the fluid is doing in an experimental pipeline. The loss function sort of takes the part of the signal transduction step. So now that I've told you how to train this model, I'll give you a quick example in practice. So here I've generated some synthetic training data from a known constitutive equation. I'm generating 8 oscillatory waveforms to train on, and using some nifty packages in the Julia language to do the training. And then I'm going to ask the model to predict 3 test tasks. So the first test task, and I should note that the training data, I'm just retaining one of the off-diagonal elements of the stress tensor, so the shear stress. And that's all the model's going to see during training. And I'm going to ask it to predict the shear stress in a different oscillatory experiment that's at a frequency that we didn't see in the test data, or in the training data. I'm also going to ask it to predict different components of that stress tensor, so this time diagonal components, which it never saw during training. And I'm going to ask it to predict the response to a completely different flow protocol, which is this transient one. So before training, as expected, the model misses pretty badly on some of these test tasks. But after we train, we get really, really good performance, really close match to our synthetic data. So it's encouraging that we can actually not just interpolate between training data conditions, but also extrapolate to different observables and different flow types. Okay, so the last thing, this goal that we set out to at the beginning, was to actually be able to use one of these models in a CFD pipeline, maybe for a condition that we care about in industry. So I'm going to here show some simulations for a contraction flow. So we have some flow coming in from the left and then contracting through a smaller diameter. This kind of is representative like a polymer extrusion process that you might find in industry. And I'm going to use this nice open source CFD package called OpenFoam, which can run these nice, highly parallel, high performance simulations of these flows. And all we have to do is plug in a constitutive model for the stress, and it solves that and the Cauchy-Monomer equations basically on a Cartesian grid. So before our training data, our ground truth data here is coming from our known constitutive equation. And before any training, we miss on some key features of this flow, such as like the velocity profile at various points after the contraction. But then after training, we see that we actually get a really nice mirroring of what should be going on in the real flow. So this is very encouraging that we can actually use these models to kind of port between data that's really easy to get in a lab and scenarios that we might care about in practice. Okay, so with that, it's time for some thank yous. Of course, first to the CSGF. Not only for like a bunch of individual support that I've gotten from many people in this organization, and of course from the Krell staff, but for the financial support to actually pursue things that I wanted to do in my PhD, which was awesome. And then I just want to say a quick word about my advisor, Jim Swan. Jim passed away a couple years ago, but he was just an absolutely excellent mentor. And we talk about the financial support to do the things we want, but it's another thing altogether to have a person who gives you the intellectual and emotional support to actually go and achieve those things. And Jim was exactly that person, so I'm very fortunate to have worked with him for as long as I did. So with that, I'll conclude and happy to take any questions.